Look up at the sky on a clear night. Pick any star. Now ask yourself a question that seems simple, but turns out to be one of the most disturbing questions in all of physics. Why hasn't anyone come from there? Not why haven't we heard from them? Why hasn't anyone arrived? We've been running radio telescopes since 1960. Project Ozma, SETI, the WOW signal that turned out to be nothing confirmed. 65 years of listening, and the universe has been completely, absolutely, eerily quiet. Most people shrug and say space is big, distances are enormous, it takes too long to get here. And they're right that space is big, but they've stopped asking the next question, which is the interesting one. Because here's the thing. The galaxy is 13 billion years old. Life on Earth took about 4 billion years to produce something that builds radio telescopes. That means if life appeared somewhere else even a billion years earlier than it appeared here, which on galactic timescales is not a long head start, that's like arriving at a party 1 minute before someone else. That civilization has had a billion years to figure out how to travel. A billion years. We've had about 70 years of spaceflight, and we already sent probes to interstellar space. What does a billion-year-old technology look like? So the silence isn't just odd. The silence, when you actually do the arithmetic, is a physics problem. And I want to walk you through what the physics actually says, because most of the popular explanations are either incomplete or just wrong. Let's start with the thing everyone points to first, the distances. The nearest star to our Sun is Proxima Centauri, 4.2 light-years away. A light-year is the distance light travels in 1 year, and light moves at 299,792,458 meters per second. So 4.2 light-years is about 40 trillion kilometers. Our fastest spacecraft Voyager 1 is moving at roughly 17 kilometers per second, which is extraordinarily fast by any human standard. We launched it in 1977, and it only just left the solar system, and at that speed reaching Proxima Centauri would take about 73,000 years. So people say, well, a sufficiently advanced civilization would build faster ships, and that's fair. Voyager wasn't built for interstellar travel. Let's think about what faster actually means, and what physics has to say about it. The first serious constraint comes from a set of experiments done in the late 1800s. Albert Michelson and Edward Morley in 1887 built an extremely precise instrument to measure how the speed of light changed depending on which direction you measured it. The Earth moves around the Sun at 30 kilometers per second, so if light was like sound, if it traveled through some medium and your speed relative to that medium mattered, they should have seen a difference. They found no difference. Zero. The speed of light came out the same regardless of the direction, regardless of how Earth was moving. This wasn't a small result. This broke physics at the time. It took Einstein in 1905 to explain what it actually meant. The speed of light isn't just fast, it's a fundamental limit. It's built into the structure of space and time themselves, and the consequences of that are strange. When you push an object faster, you put energy into it. That energy increases the object's momentum, and in everyday life, more momentum means more speed. But as you approach the speed of light, something changes. The energy you're adding doesn't all go into making the object faster. Increasingly, it goes into making the object heavier. Its effective mass increases, and because its mass is increasing, it takes more force to accelerate it further, which increases its mass more, which takes more force, and so on. By the time you're at, say, 99% the speed of light, your object is roughly 7 times heavier than it was at rest. At 99.9%, come about 22 times heavier. At 99.999%, come about 22 times heavier. You're looking at a factor of over 700. To reach exactly the speed of light, the mass would become infinite. Infinite mass requires infinite force. There is no engine in the universe that provides infinite force. This isn't a technology limitation. This is the geometry of space-time saying no. Now, the engineers in the audience are already thinking, fine, we don't need light speed. 10% light speed would be remarkable. Let's think about what that actually costs. A reasonable interstellar spacecraft, not an ark for 1 million people, just a modest exploratory vessel, say 1,000 metric tons, which is smaller than a naval destroyer, traveling at 10% the speed of light, has a kinetic energy of approximately 450 quadrillion joules, 4.5 times 10 to the 17th joules. For reference, the entire global energy consumption of humanity in a year is about 6 times 10 to the 20th joules, so that's roughly 1,000th of our annual energy budget, just to get to 10% light speed. That doesn't sound catastrophic until you remember you have to decelerate at the other end. Same energy again. And you need reaction mass. Something to push against, which means you're carrying fuel, and the fuel has mass. And accelerating the fuel requires more fuel, and that fuel requires more fuel. This is the Tsiolkovsky rocket equation, derived in 1903, and it's vicious. The mass of fuel you need grows exponentially with the velocity you want to achieve. For a conventional rocket trying to reach even 10% light speed, you'd need a fuel-to-payload ratio so large that the numbers become, without exaggeration, larger than the observable mass of the solar system. So you need exotic propulsion, laser sails, antimatter drives, fusion engines, and physicists have thought seriously about all of these. The antimatter option is the most energy-dense fuel we know of. Matter-antimatter annihilation converts mass directly to energy with 100% efficiency, which is the maximum the universe allows. To accelerate our 1,000-ton ship to 10% light speed with antimatter, you'd need on the order of 5,000 tons of antimatter. We currently produce about 10 nanograms of antiprotons per year at CERN at an energy cost of trillions of dollars per nanogram. We are not engineering our way around this problem in any foreseeable time frame. But set the energy problem aside for a moment, because relativity gives something back that's worth understanding. It's called time dilation, and it's real. We measure it in particle accelerators every day. When you move fast, time slows down for you relative to someone standing still. At 99% the speed of light, 1 year of your time corresponds to about 7 years back on Earth. At 99.9%, 1 year of your time is about 22 years on Earth. At 9.9.9.9.9% the speed of light, you age 1 year while Earth ages 700 years. This means, in principle, a crew traveling at extreme speeds experiences much less time than the journey would take at rest. The galaxy is 100,000 light-years across. At 99.999% the speed of light, a human crew could cross the entire galaxy in something like a century and a half of their own subjective time. The galaxy is crossable in a human lifetime if you can reach those speeds. But the energy required to accelerate a ship to 99.999% light speed is so absurdly enormous that it doesn't change the conclusion, it sharpens it. Time dilation doesn't help you with the energy problem. You still need to throw energy at the ship in the quantities we're talking about. And there's another problem that most people don't mention. At those speeds, space isn't empty. The interstellar medium contains about 1 hydrogen atom per cubic centimeter on average. That sounds negligible. At 99% the speed of light, it isn't. Those atoms are hitting your spacecraft with the energy of cosmic rays, high-energy radiation that damages electronics, destroys materials, and kills biological organisms. You need shielding, and shielding has mass, and mass requires more energy to accelerate. More seriously, the cosmic microwave background radiation, which is the thermal glow left over from the Big Bang and exists everywhere in the universe, gets blue-shifted to higher and higher frequencies as you go faster. At sufficiently high speeds, we're talking very close to the speed of light, that gentle background radiation becomes a lethal flood of gamma rays. Space itself at those speeds is trying to kill you. There are no known physics that get you around these constraints. Wormholes appear as solutions in Einstein's equations of general relativity, but they require something called exotic matter, material with negative energy density, to hold them open. We have no evidence that exotic matter exists in the quantities required, or in any usable form at all. The Alcubierre warp drive, proposed in 1994, requires energy on the order of the mass energy of Jupiter, and recent analyses suggest it can't be controlled and may violate causality. These aren't engineering challenges waiting for clever solutions. They're physics problems where the physics hasn't cooperated. So when Enrico Fermi sat down to lunch at Los Alamos in 1950 and asked, "Where is everybody?" he was asking a question that has gotten more puzzling, not less, as we've understood the physics better. Because here's the arithmetic he was doing in his head. The Milky Way has roughly 200 to 400 billion stars. Astronomers now know from the Kepler Space Telescope and other surveys that most stars have planets, and a significant fraction have planets in the habitable zone where liquid water can exist. Conservative estimates put the number of potentially habitable planets in our galaxy in the billions. The galaxy has been forming stars for 10 billion years. Even if intelligent life is rare, even if only 1 in a billion habitable planets develops a civilization, that still gives you hundreds of civilizations with billions of years of potential development time. And here's the key calculation. Even traveling slowly, at 1% the speed of light, which requires serious energy, but not the absurd quantities needed for relativistic travel, a civilization could colonize the entire galaxy in roughly 10 million years. You spread to nearby stars, establish colonies. Those colonies spread further, in a wave of expansion across 100,000 light years. 10 million years sounds like a lot, but the galaxy is 10 billion years old. That expansion takes 0.1% of the galaxy's lifetime. It should have happened 1,000 times over. And yet, nothing. No megastructures detectable around distant stars at the scale we'd expect from a galactic civilization, harvesting stellar energy. No signals, no visitors, no artifacts in our solar system, which we've now surveyed reasonably well. The absence is remarkable. People propose explanations. They're hiding the zoo hypothesis, the idea that advanced civilizations deliberately avoid contact with primitive ones. It's a nice story, but think about the statistics. You'd need every single civilization in the galaxy, across billions of years, to independently agree to maintain perfect silence toward us. One civilization defecting from that agreement would change everything. You can't maintain that kind of coordination across species that have never met. There's the dark forest hypothesis. Civilizations hide because revealing yourself is dangerous, since any civilization you contact might destroy you. Again, nice story. But even in that scenario, you'd expect evidence of civilizations destroying each other, energetic events, disrupted stars, something visible. We see none of that at the scale expected. These aren't explanations. They're renamed mysteries, dressed in narrative clothes. The serious answers come down to three possibilities, and none of them are comfortable. First, life capable of developing technological civilizations is extraordinarily rare. Maybe the origin of life is common, but the sequence of events that led from single-celled organisms to creatures that build radio telescopes required a specific chain of accidents. The right moon to stabilize the planet's axle, the right history of mass extinctions to clear ecological niches, the specific evolutionary pathway to large brains, and that chain happens almost never. In this case, we might genuinely be alone, or nearly so in the galaxy. Second, the energy and physics constraints on interstellar travel are so severe that no civilization ever manages expansion, regardless of how advanced they become. You can have a civilization that's 1 billion years old and still stuck in its home solar system, because the physics of moving between stars at meaningful speed simply doesn't permit it at any scale a civilization can actually achieve. The universe is built in a way that keeps things separate. Third, and this is the one that should keep you up at night, there's something ahead of us on the development path that terminates civilizations before they achieve interstellar capability. Some filter that every civilization hits and almost none survive. It could be nuclear war, engineered pandemics, climate collapse, some failure mode of artificial intelligence, or something we haven't thought of yet. The disturbing part isn't that this filter exists. The disturbing part is this: if we don't see evidence that the filter is behind us, if we discover microbial life on Mars, which would suggest that the origin of life is common and not the rare event, then statistically the filter is probably ahead of us. We're approaching it right now. This is what the Drake equation, which Frank Drake wrote on a blackboard in 1961 to organize a discussion at Green Bank Observatory, was really trying to do: not calculate a precise number, but identify where our ignorance lives. We now know several of the early terms reasonably well. Stars are common, planets are common, habitable planets are probably common. The uncertainty is entirely in the later terms. How often does life develop? How often does it become intelligent? How long do civilizations last? And the Fermi silence is evidence, indirect but real, that somewhere in that chain something goes wrong almost every time. What does this change about how you should think about your situation? You're sitting on a planet around an ordinary star, one of hundreds of billions in a galaxy that's been around for 10 billion years, and as far as we can tell, nothing like you has ever managed to spread beyond its home system. Either you're among the first, which requires a specific explanation for the timing, or you're among the rare survivors of a filter most don't pass, which requires humility about what comes next. Now, the physics is honest about what it can and can't tell us. It tells us the speed of light is a real barrier, confirmed by a century of experiments from Michelson-Morley to particle accelerators at CERN that push electrons to 99.9999999% light speed and measure their increased mass directly. It tells us the energy required for interstellar travel at meaningful speeds is enormous, with specific numbers we can calculate and verify. It tells us the galaxy is old enough and large enough that if expansion were possible and common, we'd see evidence of it. We don't. What it can't tell us is which explanation is right, whether life is rare, or travel is permanently prohibitive, or something culls civilizations we don't know. That's not a failure of physics. That's physics being honest about where the data ends and speculation begins. But here's what I find remarkable. The question, where is everybody, turns out to be a window into the deepest questions about life, the universe, and whether there's something special or something terrifying about our particular moment in the history of a 13-billion-year-old galaxy. Feynman's lunch companion Enrico Fermi asked it as a throwaway remark, and 70 years later we're still doing physics trying to answer it. The universe, it turns out, is not silent because it's empty. It might be silent because the laws of physics are very, very hard to beat, or because the creatures who try to beat them don't survive the attempt. Either way, that silence you hear when you point a radio telescope at the stars, that's not just absence of signal, that's data, and what it's telling us we are only beginning to understand.